Alright, so everything we've looked at so far when it comes to probability has to do with this normal distribution. So we're talking about some sort of distribution where everything comes out perfect. But obviously we understand in real life when we're talking about probability, we're talking about statistics, things aren't going to come out perfect. We're not always going to get the ideal situation. Now the rule of big numbers is that as your trial data, as you accumulate more and more trials, for the most part, things that are supposed to come out normal will come out normal. Which means if I take a test scores of a class of 10 students, I might not see a normal distribution. But if I take test scores from 100,000 students in the state of Ohio, now I'm going to start to see that normal distribution. So those rules of big numbers apply. And what I did is I ran just a couple of heads or tails simulations. So what you can see here is the number of heads that I got in my simulation. So what it is it flips heads or tails for me 100 times, and then it does that 100 times. So you can see the outcomes, and they're all sitting, you can see the majority of them are sitting around 50, which means of those 100 flips, here you can see 50 are heads, here you can see 49, 48, and so on. So we're talking about some pretty big data here. I'm talking about flipping 100 times and then repeating that 100 times, and I'm keeping track of each of those 100. So we can start to see something that looks like normal distribution. Let's see, it starts to look a little bit like normal distribution, but obviously that's not our bell curve. Too wobbly, not the kind of curve that we're looking for. Now, so what I did is instead of doing 100 trials, okay, let's see what happens when I do 1,000 trials. So I did 1,000 trials. So it flipped heads or tails, and it told me the number of heads. It flipped 100 times, and then it did that trial 1,000 times. So we can start to see now that number, while still not perfect, because we see we've got some peaks, some valleys, some dips where there shouldn't be dips, it's starting to get pretty close to, remember, what this normal distribution should look like would be right there. So we can see as these numbers are getting bigger, we're getting a whole heck of a lot closer to our normal distribution. And obviously I'm going to do it one more time. If I do 100,000 trials, so I flip it 100 times, and I do that 100,000 times. Now we're seeing, and actually my 50 lines up pretty good, we're seeing darn near exactly what we want to see with our normal distribution. So at this point, we would pretty much be able to say, within one standard deviation would be 68% of my data. Within 2 standard deviation, 95. Within 3 standard deviation, 99.7. But the thing about that, like we just said, yes, it's great to use this stuff. Standardized tests, they use it. It gives us a really good idea. You can use a z-score from this, and you get a percentile, and you can say a lot about the information. The thing is, can't always use that. So what we're going to start working with is some numbers that aren't always going to be distributed normally. You can see here this chart, all it is a chart of ear infections. So kids' probability to have how many ear infections. It's not normal. It's not a bell curve, but we can still take a lot of information from it. So if I'm looking at 0, I've got about 14% of kids are going to have 0 ear infections. Looks like 26% of kids are going to have 1. 27% are going to have 2. 18% are going to have 3. Right around 9% are going to have 4. 4% are going to have 5. 2% are going to have 6. And now those are all numbers I approximated. Make sure they all add up to 100. So if we're looking at this, the first problem is really easy for us to answer. What's the probability a child gets 2 or more infections? Well, all I got to do is look at 2 infections and above. Right? If I add up these probabilities, so if I add up 27 plus 18 plus 9 plus 4 plus 2, that's going to give me my percentage. So those kind of things where I'm asking you to interpret data, I expect you to be able to do that. So this question here, you should have been able to do coming into this year, really, is look at a graph and add up a bunch of different numbers. Now, the second question is, how many ear infections can I expect a newborn to get by the time they turn 4? So we're going to talk about finding what is the expected value for this data. And really the expected value is almost like a weighted situation. So we're going to weigh the number of zeros, add that to the weighted value of the number of ones, add that to the weighted value of the number twos, to the weighted value of the number threes, to the weighted value of number fours, the weighted value of number fives, the weighted value of number six. Now, what do I mean by weighted? When I'm talking about the weighted value, so when we're talking about this expected value and a weighted value, I know that 14% of ear infections, or of kids, are going to have 0 ear infections. So I'm going to set that up with a weighted value. So I know it's going to be 14% are going to have 0, and that's a multiplication sign there. And you can see the weight that this is going to hold, obviously, is going to be a 0. Okay? So we're going to bring that kind of into effect here. The next one, for 1 infection, we're right about at 26%. So we're going to do a weighted value. We'll take that 26%. At 1 would be 0.26. So that's its weighted value, or its expected value. 27% would have 2. So we're going to do the same thing. 0.27 would be a 2. So its weighted value is a 0.54. So it takes into account both the percentage and the number that we're looking at, which is number of ear infections. For number 3, I'm at about 18%. So I'll have 0.18, and I'm going to multiply that by a 3, which is also going to come out as a 0.54. 4, I'm right around 9%, so I'll have 0.09, and it's a 4, so it's a weighted value of 4, so that's going to be about 0.36. My weighted value for 5, I'm going to take the percentage, which is 0.4, and the number that I'm looking at, which is 5 infections. That'll be a 0.20. And then the last one was 6, and it looks like it's about 2%. So we'll say we're at 0.02 times a 6, and that should be equal to 0.1. Let's get a 2 over there, 0.12. So these are now my expected values, or my weighted values, I should say. So my weighted value for a 0 is a 0. My weighted value for the 1, 26% would get a 1, so that's 0.26. 27% would have a 2, so I did 0.27 times 2, and so on and so on. And that gives me this weighted value. Now what I want to do is, to find this expected value, I'm just simply going to add up all of these weighted values. And so if I add these weighted values up, I do 0 plus 0.26 plus 0.54 plus 0.54 plus 0.36 plus 0.20 plus 0.12. I come up with a value of 2.02. Now what is this value? This is what we call the expected value. This, based on this data, based on these percentages, and based on what this is telling me, this is how many ear infections I could expect a newborn to get, based solely on this data. So it takes into account everything we saw up here, and it weights each of these values based off of the percentage that we've seen, and it comes up with a mathematical way to predict an expected value. So what I could say from this value, or from this information, is that if I had a child and it was a newborn, I could expect it to get 2.02 ear infections. Now that's a mathematical thing. Now does that mean it's going to have 2.02? No, because we've seen, or we can see up here, there's kids that have no ear infections, there's kids that have 6 ear infections, but the majority of these scores now are right around 2.02, so that expected value of 2.02 kind of makes a little bit of sense. Another thing we can look at, and really actually kind of brings it to life a little bit and makes it pretty understandable, is a 6-sided die. So a 6-sided die, you've seen them. There's 6 sides, 1 through 6. 1, 2, 3, 4, 5, 6 is how they're numbered. Each one has a 1/6 chance of being selected. So if we're going to do those outcomes, we've got to weigh their possibility of happening and multiply that by what they are. So the 1 has a 1/6 chance. 2 has a 1/6 chance. 3 has a 1/6 chance. 4 has a 1/6 chance. 5 has a 1/6 chance. And 6 has a 1/6 chance. If I look at all these, I'm going to have 1/6. Let's add them up down and over here. 1/6 plus, this would be 2/6 plus 3/6, which would be here, plus 4/6, which is here, plus 5/6, and plus 6/6. Alright, so now I'm looking for my expected outcome. What number do I expect to roll when I see these die? And to do that, I weighted all of these. The nice thing about it, they're all weighted the same. There's a 1/6 chance. So now I can just add across the top. 1 plus 2 plus 3 gives me 6. Plus that 6 gives me 12. Plus 5 is 17. Plus 4 is 21. So I know my expected outcome up here for number 1 would be 21 out of 6, which is about 3.5-ish, right around there. Exactly 3.5 actually. So my expected value is 3.5. Now obviously that makes no sense because I cannot roll a 3.5. But mathematically that is my expected value. Now if we look at the second one, what sum might you expect if you roll the die 10 times and find the sum of all 10 rolls? So if I rolled 10 times, well, I would expect to get 3.5 each time. If I roll a 3.5 10 times, well, my sum I would expect would be a 35. So mathematically, statistically, my expected outcome is 3.5, or I'm expected to roll a 3.5, which can't happen, but mathematically that is what my expected outcome should be. And then if I repeat that roll 10 times and I add up all those sums, mathematically I should roll a 35. So that's what expected outcome is taking into consideration the probability of something happening and the value that goes along with that possibility happening. And it weighs those to give you a standard weight, and then you just add all those up and it'll tell you what your expected outcome is in any situation. What I want you guys to do for me on a piece of paper, if you would, all I want you to do is tell me what the expected value of the random variable x is. So you could think of this as ear infections, you could think of this as money won, whatever you want to think of it as, but I want you to find what is the expected value. Whoops, I didn't mean to move that. What is the expected value of the random variable x? So obviously we can see here, just as a hint, if I've got 10, 20, 30, 40, and you could see the majority is somewhere in here, I'd be expecting something in between 20 and 30, probably a little closer to 30. But that's what I want you guys to come up with. So that'll be the first thing I want you to do. I want you to do that on a piece of loose leaf. See if you can work through that on your own. If you need to work with a partner, you need to ask questions, feel free. I want each of you to turn that in to the top tray. And then I want you to pick up the worksheet. See if you can work through some of those problems. I'll be back tomorrow, and we'll make sure we work through those really for the whole class period, because I want you guys to be able to look at these, and I want you to see a bunch of different possibilities. So see if you can find the expected value. Now, if I come in tomorrow and you guys have questions on this, then we'll start with this, and then we'll go to that worksheet. All right, but try and get this worksheet done, get in value for the expected value here, and then work on that worksheet. Stay busy. Make sure we get something done today. Thank you.